Mars. We've been sold a dream. Gleaming colonies, domed cities, humanity's glorious backup plan. Elon Musk promises it. NASA plans for it. Movies romanticize it. But here's what the data actually shows. Mars isn't humanity's salvation. It's a radiation-soaked death trap disguised as hope. Today we're dismantling the Mars colonization fantasy with hard science, real mission data, and uncomfortable truths that billionaires don't want you thinking about. If you're fascinated by the mysteries of space, hit that subscribe button and give this video a like. It helps me continue bringing you content that challenges everything you thought you knew about the cosmos. Now let's get started. Let's start with something nobody talks about enough. Radiation. Not the kind you get from a medical X-ray or even from spending too much time in the sun. I'm talking about cosmic radiation and solar particle events that would literally cook your DNA from the inside out. Earth sits inside a protective bubble. Our planet's magnetic field, generated by the churning molten iron in our core, creates an invisible shield called the magnetosphere. This shield deflects most of the deadly charged particles streaming from the sun and from deep space. It's been protecting life on Earth for billions of years. And we take it completely for granted because we can't see it, feel it, or directly perceive it in any way. Mars doesn't have this protection. About 4 billion years ago, Mars had a magnetic field just like Earth. Scientists know this because NASA's MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, which has been orbiting Mars since 2014, detected magnetic field remnants frozen in ancient Martian rocks. These magnetic signatures tell a story of a world that once had the same protective shield we enjoy on Earth. But then something catastrophic happened. Mars's core cooled. The magnetic dynamo shut down. The protective bubble collapsed. And for the past 4 billion years, Mars has been getting bombarded by radiation that would be instantly lethal to unprotected humans. Here's what that actually means in practical terms. The Curiosity rover, which has been exploring Mars since August of 2012, carries an instrument called the Radiation Assessment Detector. This device measures exactly how much radiation hits the Martian surface every single day. The data is shocking. On Mars, you'd receive about 200 millisieverts of radiation per year just standing on the surface. To put that in perspective, the average person on Earth receives about 3 millisieverts per year from natural background radiation. Astronauts on the International Space Station, which orbits within Earth's protective magnetosphere, receive about 50 to 200 millisieverts during a 6-month mission, and that's already considered a serious health concern that NASA monitors extremely carefully. 200 millisieverts per year on Mars means that within just a few years of living on the surface, you'd accumulate radiation doses that significantly increase your cancer risk. The European Space Agency has calculated that a human on Mars would have roughly a 5% increase in lifetime fatal cancer risk for every year spent on the surface. Stay there for 10 years? That's a 50% increased risk of dying from radiation-induced cancer. And that's just the baseline. That's on a calm day when the sun is behaving nicely. Now let's talk about solar particle events. The sun periodically releases massive bursts of charged particles called coronal mass ejections. These events happen when magnetic field lines on the sun's surface tangle, snap, and release enormous amounts of energy. When one of these eruptions happens, billions of tons of solar material get hurled into space at speeds of several million kilometers per hour. On Earth, we barely notice these events because our magnetosphere deflects the particles. You might see more intense auroras. The northern and southern lights become more active and visible at lower latitudes. Occasionally, a really powerful solar storm might disrupt satellite communications or power grids, but we're fundamentally protected. On Mars, there's no protection. When a coronal mass ejection hits Mars, the full force of that radiation slams directly into the surface. In September of 2017, a solar particle event hit Mars, while multiple spacecraft were monitoring the planet. The MAVEN orbiter, the Curiosity rover, and the Mars Odyssey spacecraft all measured radiation levels. During this single event, surface radiation spiked to levels that would have been immediately dangerous to any humans on the surface. Scientists calculated that an astronaut caught outside during that storm would have received a radiation dose equivalent to about 30 chest X-rays in a single event, lasting a few hours. Now imagine you're part of a Mars colony. You're outside performing maintenance on solar panels, checking equipment, doing the thousands of tasks that would be necessary to keep a settlement running. Suddenly, instruments detect an incoming solar storm. You have maybe 30 minutes to an hour of warning before the radiation arrives. Can you get to shelter in time? What if you're kilometers away from your habitat? What if your rover breaks down? This isn't hypothetical danger. This is measured, documented, real radiation that would kill you or cause severe radiation sickness if you receive too much exposure. And these solar events are unpredictable. The Sun goes through 11-year activity cycles, with solar maximum periods featuring many more coronal mass ejections and solar flares. But even during solar minimum, the quiet period, dangerous events can still occur without warning. Now, you might be thinking, okay, radiation is bad, but we can just build better shielding, right? We'll construct underground habitats or cover our buildings with meters of Martian soil for protection. That's the standard response, and it's not wrong exactly. Shielding does work. Pile enough mass between you and the radiation source, and you can reduce exposure to safer levels. But consider what that actually means for a Mars colony. Every single habitat would need to be either underground or buried under several meters of regolith, Martian soil and rock. Every corridor connecting buildings would need the same protection. Every greenhouse where you grow food would need shielding, but not so much that it blocks all the sunlight your plants need. Every workspace, every laboratory, every common area, all buried or shielded with tons of material. This isn't just an engineering challenge. It's a logistical nightmare that multiplies the cost, complexity, and resource requirements of everything you build. It means that humans on Mars would spend virtually all their time underground or in heavily shielded structures, venturing to the surface only when absolutely necessary, and only during periods of low solar activity. Picture that existence. You travel 40 million to 400 million kilometers, depending on where Earth and Mars are in their respective orbits, spend 6 to 9 months in a cramped spacecraft, arrive at Mars full of hope and excitement about exploring a new world, and then spend the rest of your life living in underground bunkers because the surface wants to kill you. That's not the inspirational vision of Mars colonization we see in the promotional materials. That's a grim, claustrophobic existence that would test the psychological limits of even the most motivated colonists. And radiation is just the beginning of Mars's problems. Let's talk about something even more fundamental than radiation: the atmosphere. Or more accurately, the almost complete lack of one. Mars has an atmosphere so thin it might as well not exist for practical human purposes. Earth's atmosphere at sea level has a pressure of about 101,000 pascals, which we commonly refer to as 1 atmosphere or 1 bar of pressure. This is the pressure your body evolved to function within. Your cells, your blood, your entire physiology is calibrated for this specific pressure environment. Mars's atmosphere has a surface pressure of about 600 pascals. That's roughly 0.6% of Earth's atmospheric pressure. To put that in perspective, the summit of Mount Everest, the highest point on Earth, where the air is so thin that climbers need supplemental oxygen and can only survive for brief periods, has an atmospheric pressure of about 34,000 pascals. That's still more than 50 times thicker than the Martian atmosphere. Mars's atmosphere is so thin that it's actually below the Armstrong limit. This is the altitude, about 19,000 meters on Earth, where atmospheric pressure becomes so low that water boils at human body temperature. Above the Armstrong limit, the fluids in your body would literally start to boil if you were exposed to the environment without a pressure suit. This means you can never, ever step outside on Mars without wearing a full pressure suit. Not for a second, not for any reason. The moment your body is exposed to the Martian atmosphere, the water in your tissues begins to vaporize. Your blood doesn't boil in the dramatic Hollywood sense, it's more that dissolved gases come out of solution and your body fluids start to vaporize. You'd lose consciousness within about 15 seconds, and die within a minute or two. Compare this to other hostile environments humans have learned to work in. Antarctica is brutally cold, but you can survive outside with appropriate cold weather clothing. You don't need a pressure suit. The deep ocean requires specialized equipment, but submarines can use relatively simple pressure hulls. High-altitude mountaineering is dangerous, but climbers can acclimatize and function, albeit with difficulty and supplemental oxygen. Mars is different. Mars requires every single human to be wearing a complex pressure suit every single time they step outside. These aren't simple spacesuits like we use for spacewalks near Earth. They need to be durable enough for daily use, flexible enough for real work, reliable enough that a malfunction doesn't mean instant death, and maintainable with the limited resources available on Mars. NASA's current spacesuit designs are marvels of engineering, but they're also incredibly complex, expensive, and high maintenance. Each suit costs millions of dollars and requires extensive support infrastructure. They're designed for occasional use in space, not for daily wear in a dusty, abrasive environment. Developing suits that could be manufactured on Mars, maintained with local resources, and used reliably for years is an unsolved engineering challenge. And here's something that makes this even worse: Martian dust. The Spirit, Opportunity, and Curiosity rovers have all sent back extensive data about Martian dust, and it's nasty stuff. Unlike Earth dust, which gets rounded and smoothed by water and wind over time, Martian dust particles are sharp and angular. They're also incredibly fine, much finer than talcum powder, and they get into everything. The dust is also highly oxidized, meaning it's chemically reactive. Some scientists compare it to bleach or drain cleaner in terms of its potential toxicity. When the Phoenix lander analyzed Martian soil in 2008, it found perchlorates, chlorine compounds that are toxic to humans even in small amounts. Perchlorates interfere with thyroid function and can cause serious health problems with chronic exposure. Now imagine trying to maintain an airlock system where people are constantly moving in and out wearing dusty spacesuits. No matter how careful you are, some of that dust comes inside. It gets on surfaces, floats in the air, gets breathed in by colonists. Over time, everyone in the habitat would be exposed to these toxic compounds. The long-term health effects could be devastating. The Mars rovers have experienced another problem with the dust. It accumulates on solar panels, reducing power generation. The Opportunity rover actually died in 2018 when a massive dust storm covered its solar panels, and it couldn't generate enough power to keep its systems running. For a human colony dependent on solar power, and Mars colonies would almost certainly rely heavily on solar energy. Dust accumulation is a constant threat that requires regular maintenance. More time outside, more exposure to radiation, more wear on spacesuits, more opportunities for something to go wrong. Let's talk about water. Mars needs water for human survival, and the good news is that Mars definitely has water. We've known this for certain since the Mars Reconnaissance Orbiter detected massive subsurface ice deposits using ground-penetrating radar. The Phoenix lander confirmed water ice at its landing site in the northern polar region in 2008. The Curiosity rover has detected hydrated minerals, rocks that contain water molecules locked in their crystal structure, throughout its traverse of Gale Crater. More recently, in 2018, the European Space Agency's Mars Express orbiter used radar to detect what appears to be a lake of liquid water beneath the southern polar ice cap. This was exciting news because liquid water is essential for life as we know it. The lake sits about 1.5 kilometers below the ice surface and appears to be kept liquid by high concentrations of dissolved salts, the same perchlorates we talked about earlier, which lower water's freezing point. So Mars has water. The problem is accessing it. The ice deposits identified by orbiters are typically buried under meters or even hundreds of meters of soil and rock. Excavating that much material with the limited equipment available to early Mars colonies would be extraordinarily difficult. You'd need heavy machinery, reliable power systems, and ways to prevent excavated material from contaminating your habitat or equipment. The subsurface liquid water lake sounds promising until you realize it's 1.5 kilometers down, under the polar ice cap, in one of the coldest regions of an already frigid planet. Drilling through that much ice with limited resources is currently beyond our technological capability, even on Earth in similar environments, let alone on Mars, where every piece of equipment has to be shipped from Earth at enormous cost or manufactured locally with extremely limited industrial capacity. There are easier sources of water on Mars. The atmosphere contains water vapor, and you could extract it using dehumidification systems. The problem is that Martian air is incredibly dry. Even though the relative humidity can reach 100% in some locations during Martian morning, the absolute amount of water in the air is tiny because the atmosphere is so cold and thin. You'd need to process vast volumes of air to extract meaningful amounts of water. Another option is processing hydrated minerals, essentially baking water out of rocks. The Curiosity rover's sample analysis at Mars instrument has done exactly this with soil samples, heating them to several hundred degrees Celsius and capturing the released water vapor. This works, but it's energy-intensive and requires processing huge amounts of soil to extract relatively small amounts of water. The most accessible water source is probably surface or near-surface ice in the polar regions or mid-latitude ice deposits that have been identified by orbital radar. But these locations present their own challenges. The poles are extremely cold, even by Martian standards. Mid-latitude ice deposits would be more accessible, but you'd still need to excavate them and transport the ice or melt it on site. Every single drop of water used by a Mars colony would come at the cost of significant energy and effort. Recycling would need to be extraordinarily efficient, far better than what we achieve on the International Space Station, which already recycles about 93% of water. Every shower, every toilet flush, every bit of water used for growing food would need to be captured, filtered, purified, and reused. Any water lost to leakage or inefficient recycling would need to be replaced through the difficult extraction processes we just discussed. This brings us to food. Humans need to eat, and shipping food from Earth is prohibitively expensive for anything beyond initial supply missions. A permanent Mars colony needs to grow its own food. This means agriculture on a planet that has never supported life. Martian soil, or regolith, as planetary scientists call it, lacks organic matter. Earth soil is full of decomposed plant and animal material, microorganisms, nutrients built up over millions of years of biological activity. Martian regolith is sterile mineral dust. To grow anything in it, you'd first need to add nutrients, organic matter, and beneficial microorganisms. Remember those perchlorates we mentioned? They're throughout the Martian surface. The Phoenix lander found them. Curiosity found them. They're everywhere. These compounds are toxic to plants at high concentrations and toxic to humans even at low concentrations. Any regolith used for agriculture would need to be treated to remove or neutralize perchlorates before it could safely grow food. Some scientists have experimented with growing plants in simulated Martian soil here on Earth. Researchers at Wageningen University in the Netherlands created soil mixtures based on data from Mars landers and successfully grew crops including tomatoes, peas, and radishes. This sounds encouraging until you learn the details. The experiments used Earth-based simulated soil that approximated Martian mineral composition but didn't include perchlorates at realistic concentrations. The plants were grown in Earth's atmosphere with normal pressure, temperature, and humidity. They received Earth sunlight, which is about 44% more intense than sunlight on Mars due to the greater distance from the Sun. And the whole operation took place in a controlled laboratory with stable power, temperature regulation, and constant human monitoring. Replicating those conditions on Mars is a completely different challenge. You need pressurized greenhouses with artificial lighting to supplement the weaker sunlight. You'd need heating systems to maintain temperatures suitable for plant growth. Mars's average temperature is minus 63 degrees Celsius, far below what any Earth crop can tolerate. You'd need humidity control, air circulation, pollination systems, since there are no insects on Mars, and constant monitoring to prevent disease or pest problems in your sealed growing environment. All of this requires energy, lots of energy. And where does that energy come from on Mars? Solar panels work, but they're less efficient on Mars due to the greater distance from the Sun and the constant dust accumulation problem. You'd need regular cleaning, which means regular EVAs, extravehicular activities, spacewalks, which means more radiation exposure and more wear on equipment. Nuclear power is the other option. Small modular reactors could provide reliable baseline power for a Mars colony regardless of sunlight or dust storms. NASA has been developing kilopower reactors specifically for space applications. Small fission reactors that could generate about 10 kilowatts of electrical power for 10 years or more. These would be ideal for Mars bases. The catch? You're now operating nuclear reactors on another planet with limited spare parts, limited expertise if something goes wrong, and no possibility of emergency help from Earth. Modern nuclear reactors on Earth are incredibly safe due to multiple redundant safety systems, trained operators, and the ability to bring in experts and equipment if problems arise. On Mars, you're on your own. A reactor malfunction could doom an entire colony. Let's talk about something even more insidious: the low gravity. Mars has about 38% of Earth's surface gravity. You'd weigh roughly 1/3 of what you weigh on Earth. This might sound fun, and certainly the ability to jump higher and lift heavier objects more easily has appeal. But the human body didn't evolve for low gravity, and the consequences are severe. We've learned a lot about low gravity effects from astronauts on the International Space Station, which experiences microgravity, essentially weightlessness. Astronauts lose bone density at a rate of about 1 to 2% per month. Muscle mass decreases. The cardiovascular system weakens because the heart doesn't have to work as hard to pump blood. Vision problems develop as fluid shifts toward the head. The immune system becomes suppressed. When astronauts return to Earth after 6 months in space, they need weeks or months of rehabilitation to recover. Some effects, particularly bone density loss, may never fully reverse. Astronaut Scott Kelly spent 340 days on the ISS from 2015 to 2016 as part of NASA's twin study, and years later, researchers are still documenting long-term changes to his body and even his gene expression patterns. Now, Mars isn't microgravity. It has 38% of Earth's gravity. That's something. But we don't actually know if it's enough. We have extensive data on 1G, Earth gravity, and on 0G, microgravity in orbit. We have almost no data on anything in between. Nobody has ever lived for extended periods at lunar gravity, which is 17% of Earth's, or at Martian gravity. There's a real possibility that 38% gravity isn't sufficient to maintain human health long term. Maybe you need at least 50% Earth gravity, or 70%, or 90%. We simply don't know. And we won't know until someone actually tries living on Mars for months or years and we see what happens to their bodies. Here's the nightmare scenario. A colony is established. People live on Mars for several years, and we discover that prolonged exposure to Martian gravity causes irreversible health problems. Maybe bone density drops to dangerous levels. Maybe the cardiovascular system weakens to the point where colonists could never return to Earth because their bodies couldn't handle 1G anymore. Maybe pregnancies become impossible or result in developmental problems for children gestating in low gravity. Some of these concerns aren't speculation. They're educated projections based on what we know about human physiology. The cardiovascular system, for instance, is finely tuned to Earth's gravity. Your heart has to pump blood upward against gravity to reach your brain. Stand up too quickly, and you might feel dizzy as blood pressure momentarily drops. That's your body struggling momentarily to maintain blood flow against gravity. In lower gravity, the heart doesn't work as hard. Over time, the cardiovascular system adapts to the reduced workload. The heart muscle may weaken, blood vessels may lose tone, red blood cell production may decrease. An astronaut returning from the ISS has to be carefully monitored during re-entry and after landing because their cardiovascular system has adapted to microgravity and now must readjust to Earth's gravity. For Mars colonists, the question becomes, what happens to someone born on Mars who has never experienced Earth gravity? Their entire cardiovascular system develops in 38% gravity. Could such a person ever visit Earth? Would 1 g be crushing to them, the way 2 or 3 Gs are exhausting for us? Might it be medically dangerous or even lethal? This raises profound ethical questions about having children on Mars. If Martian-born humans can't safely return to Earth due to physiological adaptations to lower gravity, you're creating a population that's permanently trapped on Mars. They didn't choose to be born there. They didn't consent to never being able to visit the planet where their species evolved. Are we ethically justified in creating such a population? Let's talk about the psychological challenges. Antarctica provides our best analog for isolated, confined environments with small populations. Research stations in Antarctica house scientists and support staff for extended periods, typically 6 months to a year. Despite careful psychological screening, despite the fact that everyone volunteering for Antarctic duty knows what they're getting into, despite the knowledge that you can leave when your rotation ends, psychological problems are common. Winter over syndrome affects people stationed at Antarctic bases during the austral winter, when the sun doesn't rise for months and outdoor temperatures make it dangerous to venture far from the station. Symptoms include depression, irritability, insomnia, cognitive impairment, and interpersonal conflicts. The phenomenon is so well documented that Antarctic programs specifically prepare for it. Now consider Mars. The isolation is far more extreme. Antarctica is still on Earth. You can communicate with family and friends in real time. You know that in a true emergency, a rescue mission might be difficult, but is at least theoretically possible. You know your tour of duty ends on a specific date, and you'll return home. Mars communication has a time delay, ranging from about 4 minutes at closest approach to 24 minutes at the farthest points in the planet's orbits. A conversation with someone on Earth involves sending a message, waiting 8 to 48 minutes for a response, then waiting another 8 to 48 minutes for your reply to reach them. You can't have a real-time conversation. No video calls with family. No instant messaging. Everything is delayed. There's no emergency rescue. If something goes catastrophically wrong on Mars, a reactor failure, a disease outbreak, a structural collapse, nobody from Earth can help. The journey takes 6 to 9 months. By the time a rescue mission could arrive, everyone would be long dead. Mars colonists would know that they're truly on their own, responsible for solving every problem with only the resources they have available. And there's no going home, at least not easily. The trip to Mars is already expensive and difficult. The return trip is equally challenging. Mars colony missions would likely be one way for most participants, at least initially. You're not signing up for a 1-year tour of duty. You're signing up to permanently leave Earth and everyone you know, to spend the rest of your life in a hostile environment, living underground or in heavily shielded habitats, never breathing unfiltered air, never feeling rain on your face, never experiencing the countless sensory experiences we take for granted on Earth. Studies of isolated and confined environments, submarines, space stations, Antarctic research bases, Arctic expeditions, consistently show that after the initial excitement wears off, after you've been in the same place with the same people eating the same food, following the same routines, for months, psychological strain builds. Small annoyances become major irritations. Personality conflicts escalate. Motivation declines. On Earth-based missions, this is manageable because the situation is temporary. On Mars, there's no end date. You're not counting down the days until you return home. This is home now, and it will be for the rest of your life. The psychological weight of that permanence would be crushing for many people. There's also the question of purpose and meaning. Astronauts on the ISS are conducting cutting-edge research, advancing human knowledge, and contributing to space exploration. That sense of purpose helps sustain them during difficult moments. Early Mars colonists would have similar motivation. They're pioneers, establishing humanity's foothold on another planet, doing something historically significant. But what about the second generation, the third? People born on Mars who didn't choose to be there, who grow up in underground habitats, who can never experience Earth except through videos and stories. What gives their lives meaning and purpose when the novelty of being on Mars has long since faded, and it's just daily existence in a harsh, limited environment? We need to discuss something that rarely comes up in optimistic Mars colonization discussions: medical care. On Earth, we have hospitals, specialists, diagnostic equipment, pharmacies, surgical facilities, and emergency response systems. Break your leg on Earth and an ambulance arrives within minutes. Need surgery? You're in an operating room with trained surgeons, anesthesiologists, nurses, and modern equipment. Contract a serious illness? Specialists can diagnose and treat you with access to vast pharmaceutical resources. None of this exists on Mars. A colony would have limited medical personnel, maybe 1 or 2 doctors for a population of dozens or hundreds. Medical equipment would be basic, what can be transported from Earth or manufactured locally with extremely limited industrial capacity. Pharmaceuticals would need to be shipped from Earth or synthesized on Mars, both problematic options. Many medications have limited shelf lives. Antibiotics, vaccines, pain medications, and other essential drugs degrade over time, especially in the harsh radiation environment of Mars. A colony would need constant resupply of medications from Earth or the ability to manufacture them locally. Pharmaceutical manufacturing is complex, requiring precise chemistry, quality control, and specialized equipment. Establishing even a basic pharmaceutical industry on Mars would require enormous resources. What happens when someone needs surgery? A routine appendectomy on Earth is low risk with excellent outcomes. On Mars, with limited surgical equipment, limited anesthesia supplies, no access to specialists or emergency backup, and the patient recovering in a lower gravity environment that affects healing, outcomes become much more uncertain. One surgical complication, one unexpected infection, one reaction to anesthesia, and you have a dead colonist because the medical infrastructure simply isn't there to save them. Dental care presents similar problems. Tooth decay, gum disease, and dental emergencies are common on Earth, despite access to preventive care. On Mars, with limited dental equipment and expertise, a serious dental infection could become life-threatening. Root canals, extractions, crown work, all the procedures we take for granted, become difficult or impossible without proper facilities. Pregnancy and childbirth deserve special attention. We have zero data on human reproduction in reduced gravity. We don't know if conception works normally at Martian gravity. We don't know how pregnancy progresses. We don't know if fetal development occurs normally or if low gravity causes developmental problems. We don't know if childbirth is safe for mother and child in 38% gravity. Animal studies in space have shown concerning results. Experiments with pregnant rats in microgravity demonstrated disruptions in fetal development, particularly in the vestibular system, the inner ear structures responsible for balance. Pregnant rats in spaceflight experienced higher rates of complications. While Mars has some gravity, we don't know if it's sufficient for normal mammalian reproduction. Imagine being pregnant on Mars, knowing you're essentially conducting an experiment on your own body and your unborn child. No previous human has done this. There's no medical literature to consult, no experienced obstetricians who've delivered babies in Martian gravity, no understanding of what might go wrong or how to handle complications. If something goes wrong during pregnancy or delivery, the limited medical facilities on Mars might not be able to save the mother, the baby, or both. These aren't abstract concerns. If Mars colonies are going to be permanent, if they're going to be self-sustaining rather than dependent on constant resupply from Earth, people will need to have children there. The colony population needs to grow. But subjecting pregnant women and developing fetuses to an environment we know essentially nothing about, medically speaking, raises serious ethical questions. Let's examine the economics, because ultimately someone has to pay for all of this. Current estimates for sending cargo to Mars range from about $100,000 to $500,000 per kilogram, depending on the mission design and payload requirements. Every piece of equipment, every tool, every spare part, every kilogram of supplies needs to be either shipped from Earth at these enormous costs or manufactured on Mars with extremely limited industrial capacity. Building an initial Mars base that could support even a small crew of 10 to 20 people would likely cost hundreds of billions of dollars. NASA's current estimates for a crewed Mars mission, not a permanent base, just a mission to land astronauts, conduct surface operations for a few weeks, and return, range from $200 billion to $500 billion. A permanent, self-sustaining colony would cost vastly more. Where does this money come from? Government space agencies have limited budgets. NASA's entire annual budget is around $25 billion, and that's split among numerous programs: ISS operations, Earth science, planetary exploration, aeronautics research, technology development, and more. Redirecting enough funding to establish a Mars colony would require abandoning most other programs, which is politically unlikely. Private companies like SpaceX talk about dramatically reducing launch costs and making Mars colonization economically feasible. Elon Musk has stated his goal of reducing the cost per ton to Mars to under $100,000, potentially as low as $10,000 per ton, with fully reusable spacecraft. Even if these ambitious targets are achieved, and that's a big if, the total cost of establishing a meaningful colony would still be astronomical. Let's do some rough math. A small initial Mars base supporting 20 people might need 500 to 1,000 tons of equipment and supplies, habitats, power systems, life support equipment, rovers, tools, spare parts, food until local agriculture is established, and countless other necessities. At $10,000 per ton, the most optimistic projection, that's $5 to $10 million just for cargo transport. At more realistic current costs of $100,000 per ton, you're looking at $50 billion to $100 billion just to ship the initial supplies. That's before developing any of the technology, training the crew, building the spacecraft, operating mission control, or any of the other costs involved. And that's just the initial setup. The colony would need regular resupply missions for years or decades until it achieves genuine self-sufficiency, if it ever does. Who pays for this? Governments could fund it as a national prestige project, the way the Apollo program was funded during the space race, but Apollo was a short-term program with clear objectives and a definite endpoint. Mars colonization is open-ended, requiring sustained funding for decades or centuries. Political will for such long-term commitments is hard to maintain, especially when the money could address urgent needs on Earth: poverty, disease, climate change, infrastructure, education. Private funding is the other option, but what's the return on investment? Mars has no obvious economic resources that would justify the enormous cost of extraction and transport back to Earth. Some people speculate about mining rare minerals or elements, but anything you could mine on Mars could be obtained more cheaply from asteroids, which don't have the deep gravity well that makes launching cargo off Mars difficult and expensive. Tourism might generate some revenue, but the trip is long, dangerous, and uncomfortable. The market for paying customers willing to spend months in space traveling to Mars and then months on a hostile planet before months traveling back is probably very small, and those customers would need to be extraordinarily wealthy to afford tickets priced high enough to cover costs. Scientific research is valuable, but it doesn't generate direct economic returns. We learn about planetary formation, search for evidence of past life, study geology and climate in ways that inform our understanding of Earth, and develop technologies with applications back home. These are worthy goals, but they don't produce the kind of economic value that would allow a Mars colony to become financially self-sustaining. Some advocates argue that Mars colonization is insurance for humanity, a backup civilization in case something catastrophic happens to Earth. This argument has emotional appeal, but doesn't hold up under scrutiny. Any disaster that makes Earth less habitable than Mars would have to be extraordinarily severe. Mars is already a radiation-soaked, airless, frozen desert. Earth after a nuclear war, a major asteroid impact, a supervolcano eruption, or catastrophic climate change would still be far more hospitable than Mars. Even in the worst-case scenarios we can imagine for Earth, global thermonuclear war, runaway climate change, a pandemic that kills 99% of humanity, the survivors on Earth would still have breathable air, manageable radiation levels, accessible water, and a biosphere with some remaining life. Rebuilding on a damaged Earth would be immeasurably easier than trying to sustain a colony on Mars that depends on constant technological life support systems. The insurance policy argument also ignores the fact that a Mars colony wouldn't be independent of Earth for decades or possibly centuries. It would require constant resupply, technological support, and expertise from Earth. If Earth civilization collapsed, the Mars colony would die shortly afterward when resupply missions stopped arriving and critical systems failed without replacement parts or expertise to repair them. A genuine backup civilization would need to be entirely self-sufficient, capable of manufacturing everything from computer chips to pharmaceuticals, maintaining and repairing all critical infrastructure without Earth's help, and sustaining a population large enough to avoid genetic bottlenecks and maintain the knowledge base necessary for technological civilization. We're talking about thousands or tens of thousands of people at minimum with complete industrial infrastructure. The cost and difficulty of establishing that on Mars is almost incomprehensible. Now let's talk about something that gets even less attention than medical care: the legal and governmental challenges. Who owns Mars? Who has jurisdiction over colonies? What laws apply? How are disputes resolved? What happens when, not if, but when, conflicts arise between different colonies, different nations, or between colonists and Earth-based authorities? The Outer Space Treaty of 1967, which has been ratified by over 110 countries, states that outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty. In theory, no nation can claim to own Mars or any part of it. Resources extracted from celestial bodies exist in a legal gray area. The treaty says space should be used for the benefit of all countries, but it doesn't clearly address whether private companies or individuals can own resources they extract. More recent attempts to clarify space resource rights have been controversial. The United States passed the Commercial Space Launch Competitiveness Act in 2015, which grants U.S. citizens and companies rights to resources they extract from asteroids and other celestial bodies. Luxembourg passed similar legislation. Other nations have criticized these laws as inconsistent with the Outer Space Treaty spirit, if not its letter. Now imagine multiple nations or companies establishing separate colonies on Mars. Who mediates disputes? If a Chinese colony and an American colony both claim the same water ice deposit, who decides who gets access? If a SpaceX colony has a territorial dispute with a NASA base, what legal framework resolves it? If colonists declare independence from Earth governments, is that legal? Can they be stopped? Earth's history is full of colonial ventures that began with optimistic ideals and evolved into exploitation, conflict, and tragedy. The colonization of the Americas devastated indigenous populations and created societies built on slavery and inequality. The European colonization of Africa and Asia involved brutal exploitation and resource extraction. Even Antarctica, governed by international treaty, has seen territorial disputes and conflicts over resource rights. Mars colonization advocates often present it as a fresh start, an opportunity to build better societies free from Earth's problems. But humans are still humans. We'll carry our conflicts, prejudices, and power struggles with us wherever we go. Without clear legal frameworks, strong institutions, and mechanisms for resolving disputes, Mars colonies could easily become sources of conflict rather than hopeful new beginnings. There's also the question of governance within colonies. Who's in charge? How are decisions made? In the early phases, when colonies are small and dependent on Earth for survival, they'll likely operate under some form of corporate or governmental authority. Employees or astronauts follow orders from mission control. But as colonies grow and become more permanent, residents will want self-determination. They'll want to vote on policies that affect their lives. They'll want representation and rights. History shows that when distant populations feel they're being governed unfairly by remote authorities, revolutions happen. The American Revolution was sparked partly by colonist frustration with British governance from across the Atlantic. Could we see a Martian independence movement? What would that look like? Would Earth try to maintain control by force? How would that even work with communication delays and travel times measured in months? Let's consider the environmental ethics. Mars is currently a pristine, untouched world. It may harbor evidence of past life, or possibly even present life in subsurface environments where liquid water might exist. Before we start large-scale industrial development, shouldn't we thoroughly explore Mars to understand what's there? Shouldn't we preserve parts of it for scientific study? The Viking landers in the 1970s conducted the first experiments searching for life on Mars. Results were ambiguous and remain controversial. The Curiosity and Perseverance rovers have found organic molecules and evidence of past habitable environments, but no definitive proof of life. The question remains open. Did life ever arise on Mars? Does it still exist in isolated pockets? If we establish colonies and start extracting water, mining minerals, and altering the environment before thoroughly answering these questions, we risk destroying evidence before we find it. We might even inadvertently contaminate Mars with Earth life, making it impossible to ever know for certain if Mars had its own indigenous biology. Planetary protection protocols exist to prevent this. NASA and other space agencies follow strict procedures to sterilize spacecraft to avoid contaminating other worlds with Earth microbes. But a colony is different. Humans are walking biospheres carrying trillions of microorganisms in and on our bodies. Despite all precautions, we'd inevitably introduce Earth life to Mars. Some microbes would almost certainly escape containment and contaminate the Martian environment. Is this ethical? Do we have the right to potentially extinguish or contaminate another world's biology, if it exists, for our own purposes? Some argue that Mars is dead and lifeless, so contamination doesn't matter. Others argue that we should explore thoroughly before making that determination. Still, others suggest that spreading Earth life is positive, that we have a responsibility to spread biology throughout the solar system. These are profound questions without clear answers. They deserve thoughtful consideration and debate before we irreversibly alter another planet. Once we've contaminated Mars with Earth life, we can never go back. The decision needs to be made carefully, with input from scientists, ethicists, and the global community, not rushed through by companies eager to establish colonies before competitors do. Let's return to physical challenges. We haven't talked much about temperature. Mars is cold. Really cold. The average surface temperature is minus 63 degrees Celsius. Summer temperatures at the equator can reach a balmy 20 degrees Celsius during the day, but then plummet to minus 73 degrees Celsius at night. At the poles, winter temperatures drop below minus 125 degrees Celsius. These extreme temperature swings create engineering challenges. Materials expand when heated and contract when cooled. Repeated thermal cycling causes stress and eventual failure. Every seal, joint, and connection in your habitat needs to maintain integrity despite constant temperature fluctuations. Every piece of equipment needs to function reliably across a temperature range that exceeds anything we deal with on Earth. The rovers on Mars have taught us valuable lessons about these challenges. The Opportunity rover operated for almost 15 years, far beyond its planned 90-day mission, but it survived partly because NASA engineers designed it with extensive thermal protection and used radioisotope heater units to keep sensitive electronics warm during frigid Martian nights. Human habitats would need similar protection but on a much larger scale. Heating systems would need to run constantly, consuming energy and requiring reliable power sources. Any failure in heating could be catastrophic. If habitat temperature drops below freezing, water systems freeze and pipes burst. Electronics fail. Food freezes. In the time it takes to repair the heating system, the habitat could become uninhabitable. Insulation helps, but insulating a large habitat is challenging. On Earth, we often use air gaps for insulation. Think of double-pane windows. On Mars, the atmosphere is already so thin that it provides minimal insulation. Solid insulation materials would need to be thick and massive, adding to the amount of material that needs to be transported from Earth or manufactured locally. There's another thermal challenge that doesn't get enough attention: heat dissipation. Wait, didn't we just say Mars is freezing? How is getting rid of heat a problem? Here's the thing. Human activities, especially industrial processes, generate lots of waste heat. Power generation, manufacturing, computers, life support systems all produce heat that needs to go somewhere. On Earth, we dissipate heat easily because we're surrounded by atmosphere. Air carries heat away through convection. We use cooling systems that rely on evaporating water or moving air. On Mars, the thin atmosphere makes convection cooling almost useless. You can't just open a window or run a fan to cool things down. Heat dissipation has to happen through radiation or by using scarce water resources in cooling systems. This becomes a bigger problem as colonies grow and industrial activity increases. A small habitat with a few people doesn't generate much heat. A larger colony with manufacturing facilities, greenhouses with high-intensity grow lights, data centers, and hundreds of people living and working generates substantial heat that somehow needs to be radiated away into the Martian environment without freezing your cooling systems in the process. NASA has dealt with this on spacecraft and the ISS using radiator panels that emit infrared radiation to dissipate heat. Mars colonies would need similar systems, but on a much larger scale. More infrastructure, more complexity, more things that can break. Let's talk about dust storms. Mars is famous for them. We've observed dust storms from orbit and from the surface for decades. Some are localized, affecting only small regions. Others grow to encompass the entire planet, blocking sunlight and lasting for weeks or months. In 2018, a global dust storm killed the Opportunity rover. The rover ran on solar power, and as dust blocked the sun, power generation dropped to nothing. Opportunity tried to enter a low-power hibernation mode to wait out the storm, but it never woke up. Engineers believe the cold or perhaps accumulated dust damage killed it during the months-long storm. A human colony would face similar threats. Solar panels covered in dust stop generating power. If backup power systems fail or run out of fuel, life support systems shut down. Greenhouses lose light and plants die. Temperature control fails. Communication systems go offline. The colony goes dark. Nuclear power provides more reliable baseline energy that doesn't depend on sunlight, but reactors still need cooling systems, and those systems have components exposed to the environment where dust accumulation could cause failures. Redundancy helps. Multiple power systems, multiple cooling systems, extensive battery backup, but redundancy adds cost, complexity, and more things to maintain. Dust storms also limit mobility. During a storm, visibility drops to near zero. Rovers can't navigate. Humans can't venture outside safely because they can't see where they're going, and navigation systems might be compromised. The colony essentially goes into lockdown until the storm passes. If the storm lasts weeks or months, as the 2018 storm did, that's a long time to be confined with no ability to perform external maintenance, repairs, or exploration. There's a more subtle danger with dust: electrostatic charging. Martian dust particles become electrostatically charged as they blow around in the thin atmosphere and low humidity. This creates static electricity that can damage electronics, interfere with equipment, and cause dust to cling stubbornly to surfaces. The phenomenon was observed by all the Mars landers and rovers. Cameras get dust on their lenses that's difficult to remove. Solar panels accumulate charged dust that resists simple cleaning methods. For a colony, this means constant battles with dust-infiltrating seals, coating equipment, damaging electronics and contaminating habitats. It's not just an annoyance, it's a persistent threat to the technology that keeps colonists alive. We should discuss the communication delay again because it affects more than just personal conversations. The round-trip light time between Earth and Mars ranges from about 8 minutes at closest approach to 48 minutes at the farthest orbital positions. This delay makes real-time remote operation impossible. On Earth, we can remotely operate equipment anywhere on the planet with minimal lag. Doctors perform remote surgeries using robotic systems. Engineers troubleshoot problems via video conference. Experts provide guidance in real time during emergencies. None of this works with Mars's communication delay. If a critical system fails on Mars and colonists need expert help from Earth, they send a description of the problem, wait 8 to 48 minutes for the message to reach Earth, wait while experts analyze the situation and formulate a response, then wait another 8 to 48 minutes for the response to arrive. In an emergency where every minute counts, this delay could be the difference between solving a problem and dying. The delay also affects mission planning and operations. Mars rovers like Curiosity and Perseverance can't be driven in real time. Controllers on Earth program a sequence of movements, send the commands, wait for the signal to reach Mars, then wait again for telemetry to return showing what happened. This makes exploration slow and requires the rovers to have substantial autonomous capability to avoid hazards. Human explorers wouldn't need such extensive autonomy because they can make real-time decisions, but they'd still be isolated from Earth-based expertise and support in ways that increase risk. Every problem needs to be solvable with the resources, knowledge, and personnel available on Mars. There's no calling Earth for immediate help. This isolation extends to scientific research. Scientists on Earth studying Mars data can analyze results, suggest new experiments, and provide expertise, but the communication delay makes collaboration cumbersome. Mars-based researchers would need to be highly trained across multiple disciplines because they can't quickly consult with specialists on Earth. Let's examine the trajectory of getting to Mars in the first place, because the journey itself is dangerous and difficult. Mars and Earth orbit the Sun at different speeds and distances. Launch windows, periods when the planets are positioned favorably for efficient transfers, occur roughly every 26 months. Miss a launch window, and you wait over 2 years for the next one. The trip takes 6 to 9 months using current propulsion technology. That's half a year or more confined in a spacecraft with limited space, limited resources, recycled air and water, cosmic radiation exposure, and microgravity effects on your body. Astronauts arriving at Mars after 6 months in space would be weakened, their bones demineralized, their muscles atrophied, their immune systems compromised, and they'd arrive at a planet that immediately demands physical labor, unloading cargo, assembling habitats, setting up life support systems, establishing power generation, all while adjusting to Martian gravity after months in microgravity and dealing with the radiation, temperature extremes, and hostile environment we've been discussing. Advanced propulsion systems could shorten the journey. Nuclear thermal or nuclear electric propulsion could potentially cut travel time to 3 or 4 months. Even more advanced concepts like fusion drives or antimatter propulsion could theoretically reduce it further. But these technologies are decades away from practical implementation if they're achievable at all with known physics. Shorter travel times reduce radiation exposure during the journey and minimize the physiological effects of microgravity, but they require more energy, more advanced technology, and more development time and cost. They don't eliminate the fundamental challenges waiting at Mars itself. There's also the return journey to consider. If colonists ever want to return to Earth, or if we're sending astronauts on exploratory missions rather than permanent colonization, we need to launch from Mars. That means either bringing enough fuel for the return trip, which massively increases the amount of mass that needs to be sent to Mars in the first place, or manufacturing fuel on Mars using local resources. In situ resource utilization, producing fuel from Martian resources, is possible in theory. The Martian atmosphere is about 95% carbon dioxide. With energy and hydrogen imported from Earth, or extracted from Martian water, you can produce methane and oxygen through the Sabatier reaction. SpaceX's Starship design plans to use exactly this approach: land on Mars, extract water or import hydrogen, produce methane and oxygen fuel, and use it for the return journey. This sounds elegant, but it requires establishing and operating a chemical plant on Mars. You need power for the reactions. You need equipment that can extract water or process atmospheric carbon dioxide. You need storage tanks for the produced fuel. You need all of this to work reliably, because if fuel production fails, your return spacecraft is stranded. NASA's Mars 2020 mission included a small experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. MOXIE successfully produced oxygen from Martian atmospheric carbon dioxide multiple times throughout its mission, proving the concept works. But MOXIE is a small demonstration unit producing a few grams of oxygen per hour. Scaling up to produce the tons of fuel needed for a return journey is an enormous engineering challenge. Let's discuss something that might seem trivial but is actually crucial: spare parts and repairs. On Earth, if something breaks, you order a replacement part. It arrives in days or weeks. You have access to specialized tools, expert technicians, and essentially unlimited replacement options. Need a specific electronic component? Thousands of suppliers can provide it. Need a specialized tool? You can buy it or rent it. Mars has none of this infrastructure. Every spare part needs to be either brought from Earth at enormous expense and with years of advanced planning, or manufactured on Mars with extremely limited capabilities. Early colonies would have essentially no manufacturing capacity beyond basic 3D printing of simple plastic or metal parts. Complex electronics, precision components, specialized materials, all would need to come from Earth. The implications are staggering. Colony planners would need to anticipate every possible failure mode for every piece of equipment and pack spare parts accordingly. But you can't predict everything. Unexpected failures will happen. Equipment will break in unanticipated ways. And when that happens, colonists would need to improvise repairs using whatever materials and tools they have available. The Apollo 13 mission demonstrated both the ingenuity and the limitations of improvised repairs in space. When an oxygen tank exploded, threatening the crew's lives, engineers on Earth and astronauts in space worked together to build improvised carbon dioxide scrubbers using duct tape, plastic bags, and suit hoses. It worked, and the astronauts survived. But Apollo 13 had real-time communication with Earth-based experts and only needed to survive for a few days. Mars colonists would face the communication delay we discussed, and would need repairs to last for years or decades. The ISS provides another data point. Despite extensive spare parts, advanced tools, and regular resupply missions, the station has experienced numerous equipment failures requiring creative repairs. Spacesuits have developed water leaks. Life support components have failed. Computer systems have crashed. In each case, astronauts and ground controllers work together to solve the problems. But the ISS has the advantage of being just 400 kilometers from Earth, with constant communication and the ability to evacuate crew members relatively quickly if necessary. Mars colonies would be millions of kilometers from help, with communication delays and no quick evacuation option. The psychological pressure of knowing that a single critical system failure could kill everyone, and that you're responsible for preventing or fixing it with limited resources, would be immense. Manufacturing capability would eventually develop, but building an industrial base on Mars is a massive undertaking. You can't just build a factory. You need the entire supply chain. To make complex electronics, you need semiconductor fabrication facilities, which require ultra-pure materials, clean room environments, specialized equipment, and extensive expertise. To produce that equipment, you need machine tools. To make machine tools, you need metallurgy and precision manufacturing. Every step requires previous steps. On Earth, we built this capability over centuries, with billions of people contributing knowledge and labor, with abundant natural resources easily accessible, and with a breathable atmosphere and comfortable environment that didn't require constant life support. Mars starts with none of these advantages. Some advocates argue that 3D printing and advanced manufacturing technologies will accelerate the process, allowing Mars colonies to rapidly develop manufacturing capabilities. This is overly optimistic. Yes, 3D printing is amazing and useful, but current technology can only produce limited categories of objects. You can't 3D print a computer processor or a high-efficiency solar cell or a medical diagnostic device. Those require sophisticated manufacturing processes that are beyond current additive manufacturing capabilities. The colony would remain dependent on Earth for critical supplies for decades at minimum, probably much longer. This dependence creates vulnerability. What happens if political situations change on Earth and supporting the Mars colony becomes controversial? What if economic conditions make funding the expensive resupply missions difficult? What if a disaster on Earth, pandemic, war, economic collapse, disrupts the supply chain? A Mars colony that depends on Earth is fundamentally not a backup for humanity. It's an outpost that survives only as long as Earth civilization remains healthy enough and interested enough to support it. If the goal is truly to make humanity a multi-planetary species, the colony needs to achieve genuine independence, and that's far more difficult than most people realize. Let's talk about something we've touched on, but deserves deeper examination: water recycling. On the ISS, the life support systems recycle approximately 93% of water. This is an impressive achievement representing decades of engineering development. The system processes urine, sweat, and water vapor from the air, purifying everything to potable standards. Astronauts joke that today's coffee is tomorrow's coffee, which is accurate. The water cycles through human bodies and the recycling system repeatedly. Even with 93% efficiency, the ISS still requires water resupply. That 7% loss adds up over time. Fresh water gets shipped up on cargo flights to compensate for the losses. For a Mars colony, there's no easy resupply. Water would need to be extracted from Martian ice or regolith at considerable effort and energy cost. This means recycling efficiency needs to be even better than what the ISS achieves, probably 98 or 99% or higher. Every shower, every toilet use, every meal preparation, every industrial process that uses water needs to have that water captured, filtered, and purified for reuse. Any leakage anywhere in the system represents a loss that must be replaced through energy-intensive extraction. This creates pressure to limit water use, which affects quality of life. Short showers, minimal cleaning, carefully rationed water for all purposes. The psychological impact of constant resource scarcity shouldn't be underestimated. On Earth, most people in developed nations take water for granted. Turn on a tap and clean water flows. Take a long shower, water your garden, wash your car. On Mars, every drop of water has cost and value. The mental burden of constantly monitoring consumption, of knowing that waste could threaten everyone's survival, adds to the psychological stress of colony life. Air recycling presents similar challenges. Humans breathe oxygen and exhale carbon dioxide. Plants do the opposite. They take in carbon dioxide and produce oxygen through photosynthesis. In theory, a closed ecosystem with the right balance of humans and plants could maintain a stable atmosphere indefinitely. In practice, it's far more complicated. The most ambitious attempt at a closed ecosystem was Biosphere 2, built in Arizona in the late 1980s and early 1990s. The facility housed a crew of 8 people in a sealed environment with plants, soil, and recycling systems designed to maintain atmospheric balance. The first mission, lasting from 1991 to 1993, encountered serious problems. Oxygen levels declined unexpectedly as microbes in the soil consumed oxygen faster than plants could produce it. Carbon dioxide levels fluctuated wildly. Eventually, oxygen had to be pumped into the facility from outside, breaking the closure. The second mission from 1994 to 1994 was cut short after management disputes, but it too experienced atmospheric control challenges. Biosphere 2 taught us that closed-loop life support is extraordinarily difficult. Maintaining stable atmospheric composition requires precise balancing of biological and mechanical systems, extensive monitoring, and constant adjustments. And that was in a facility on Earth with backup options and the ability to open doors if things went seriously wrong. A Mars colony can't just open the doors and let in fresh air. Mechanical systems for air recycling are more controllable than biological systems but require energy and maintenance. The ISS uses chemical processes to remove carbon dioxide from the air and electrolysis to split water into hydrogen and oxygen, providing breathable oxygen for the crew. The removed carbon dioxide is typically vented overboard rather than fully recycled, though newer systems can convert some of it back to usable resources. For Mars, venting carbon dioxide outside isn't practical long-term because you'd be losing the carbon and potentially the oxygen that could be recovered from it. Full recycling requires converting carbon dioxide back to oxygen, either through plants or through chemical processes like the Sabatier reaction we mentioned earlier. Both approaches work but add complexity and energy demands. The redundancy required for life-critical systems multiplies everything. You can't have a single air recycling system because if it fails, everyone dies. You need multiple backup systems, spare parts, alternative methods, and the expertise to maintain and repair everything. The same applies to water recycling, power generation, thermal control, and every other system that keeps humans alive in the hostile Martian environment. We need to confront a reality that Mars colonization advocates rarely discuss in depth: the economic parasitism problem. A Mars colony, for decades, or possibly centuries, would be an enormous consumer of Earth's resources while producing essentially nothing of economic value in return. It would be the most expensive scientific outpost ever created, requiring constant subsidies with no prospect of financial return. Compare this to historical colonization efforts. European colonization of the Americas, while morally horrific in its treatment of indigenous populations, was economically motivated and economically viable. Colonies produced valuable resources: gold, silver, tobacco, sugar, cotton, furs. These resources could be transported back to Europe and sold for profit. Private investors funded colonies expecting financial returns and often received them. Even Antarctica, which has no native population to exploit and limited economic resources, pays for itself through scientific research grants. The research conducted there advances human knowledge in glaciology, climate science, astronomy, and numerous other fields. While expensive, Antarctic research stations are funded through existing scientific budgets and contribute to our understanding of Earth's climate systems, which has practical value. Mars offers no equivalent economic return. Enthusiasts sometimes suggest mining valuable minerals or rare elements, but the economics don't work. Any element or mineral you could extract from Mars could be obtained more cheaply from asteroids, which have comparable resources without a deep gravity, well-making launch expensive. And even asteroid mining, which would be far easier than Mars resource extraction, has yet to demonstrate economic viability despite decades of study. The fundamental problem is the cost of shipping anything between planets. Even if Mars had mountains of pure platinum sitting on the surface, the cost of mining it, refining it, launching it off Mars, and shipping it back to Earth would exceed the market value of the platinum. The only things worth shipping between planets are things that literally don't exist or can't be obtained elsewhere. And Mars has nothing Earth lacks except scientific data about Mars itself. Some people argue that Mars colonization will drive technological development that benefits Earth, similar to how the Apollo program produced useful spin-off technologies. This is true but doesn't justify the cost. We could achieve far more technological development by investing hundreds of billions of dollars directly in research and development here on Earth, where conditions are favorable and resources are abundant. The argument that we need to go to Mars to drive innovation is like saying you need to climb Mount Everest while juggling to improve your coordination. Technically true, but there are much more efficient approaches. Tourism is sometimes suggested as a revenue source, but this doesn't withstand scrutiny. The journey to Mars takes 6 to 9 months each way in cramped conditions with significant radiation exposure and health risks. The surface experience involves living in underground bunkers or sealed habitats, wearing pressure suits for any outdoor excursion, and experiencing only a limited environment. You can't breathe the air, touch the soil with bare hands, or explore freely. The total trip would take 2 to 3 years minimum due to orbital mechanics requiring you to wait for a return launch window. Who pays for this experience? What's the market price? Even if tickets cost only $1 million, vastly less than actual costs, how many people have both the money and the desire to spend years of their life on such a journey? The wealthy individuals who might afford it generally have comfortable lives they're not eager to leave for multi-year expeditions to hostile environments. Adventure tourism exists, but even extreme Earth tourism, Everest climbs, Antarctic expeditions, deep sea diving, involves much shorter durations and less risk than Mars trips. We should examine the philosophical question of why we'd choose Mars specifically as a colonization target. If the goal is establishing humanity beyond Earth, the Moon is much more accessible. It's only 3 days away rather than 6 months. Communication is near instantaneous rather than delayed by 8 to 48 minutes. Abort to Earth is possible if something goes catastrophically wrong. Apollo 13 demonstrated this. Launch windows occur continuously rather than every 26 months. Resupply is vastly cheaper and faster. Yes, the Moon has no atmosphere and less gravity than Mars, about 17% of Earth's gravity compared to Mars's 38%. But it also has water ice at the poles, confirmed by multiple missions including India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter. It has mineral resources, and most importantly, it's close enough that building infrastructure there is plausible with current technology and realistic budgets. A lunar base could serve as a testbed for technologies needed for Mars. We could develop closed-loop life support, practice in-situ resource utilization, learn to manufacture goods from local materials, and study long-term low-gravity health effects, all while remaining close enough to Earth that emergencies could be managed and costs kept somewhat reasonable. If a lunar base proves sustainable and we develop the technologies needed for true off-Earth independence, then Mars becomes a more realistic target. We'd go to Mars from a position of having solved the fundamental challenges rather than hoping to solve them while simultaneously dealing with Mars-specific problems. But Mars advocates often dismiss the Moon as uninteresting, arguing that Mars is the real prize because it has more resources, more potential for terraforming, and greater public excitement. These arguments prioritize vision over practicality. They assume that somehow, despite Mars being hundreds of times more distant and vastly more difficult to reach, we'll solve problems there that we haven't solved anywhere else. Let's discuss terraforming, since it's often presented as the ultimate goal of Mars colonization. The idea is to transform Mars into an Earth-like planet with a thicker atmosphere, warmer temperatures, and eventually liquid water on the surface, and perhaps even breathable air. If successful, Mars becomes genuinely habitable, rather than a hostile environment requiring constant life support. The scale of terraforming Mars is almost incomprehensible. Mars's atmosphere is currently less than 1% the thickness of Earth's. To reach breathable conditions, you'd need to increase the atmospheric mass by roughly 150 times. Where does all that gas come from? One proposal involves releasing carbon dioxide frozen in the Martian polar ice caps and absorbed in the regolith. Heat the planet enough and this carbon dioxide sublimes into the atmosphere, thickening it and creating a greenhouse effect that leads to further warming. The process could theoretically be self-sustaining once initiated, a runaway greenhouse effect, but one we'd intentionally create rather than trying to prevent. In 2018, researchers Bruce Jakosky and Christopher Edwards published a paper analyzing this proposal in detail. They calculated the total amount of carbon dioxide accessible on Mars, in the ice caps, in the regolith, and absorbed in minerals, and determined it's insufficient. Even if you released every molecule of carbon dioxide accessible with known technology, you'd only achieve about 7% of Earth's atmospheric pressure. That's better than current conditions, but still nowhere near breathable or even close to Earth normal. You'd remain in a pressure suit whenever you went outside. The atmospheric pressure would still be below the Armstrong limit. You wouldn't have solved the fundamental habitability problem. You'd have made conditions slightly less terrible, but still terrible. Other proposals involve importing volatiles from elsewhere in the solar system, crashing comets or asteroids rich in water ice, and frozen gases into Mars to add atmosphere. The engineering challenges are staggering. You'd need to identify suitable objects, develop technology to alter their orbits precisely, and then deliberately crash them into Mars in controlled ways that release their volatiles without destroying the infrastructure you've built. The energy and resources required would be enormous, and the timescales would be measured in centuries or millennia. Even if you somehow generated a thick atmosphere, you'd face another fundamental problem. Mars has no magnetic field. Remember, Mars lost its original magnetic field billions of years ago when its core cooled. Without that protective shield, the solar wind, charged particles streaming from the sun, gradually strips away the atmosphere. This process is slow on human timescales, but inevitable on geological timescales. NASA's MAVEN mission has directly measured this atmospheric loss. Mars currently loses about 100 grams of atmosphere per second to space. That might not sound like much, but over millions of years, it adds up. Any thick atmosphere you create would gradually disappear over geological time unless you continuously replenish it or somehow restart Mars's magnetic field. Restarting a planetary magnetic field is beyond current technology by an enormous margin. You'd need to reheat Mars's core or create an artificial magnetic field powerful enough to shield an entire planet. Some scientists have proposed placing a magnetic shield at the Mars-Sun L1 Lagrange point, a location between Mars and the Sun where gravitational forces balance, to deflect solar wind. This is theoretically possible, but would require technology and energy resources far beyond our current capabilities. The timescales for terraforming are also worth considering. Even the most optimistic estimates suggest centuries before Mars could have a breathable atmosphere. More realistic assessments put the time frame at thousands or tens of thousands of years. This assumes we develop technologies that don't currently exist, commit resources on a scale never before attempted, and maintain that commitment across hundreds of generations. Human civilization has never undertaken a project spanning centuries with continuous focus and resource commitment. Our longest-lasting institutions, certain governments, religious organizations, universities, have existed for centuries, but they've changed dramatically over time and have never maintained focus on a single enormous engineering project. The idea that we could sustain a planetary engineering effort for thousands of years requires assumptions about political stability, economic continuity, and sustained will that history gives us no reason to believe are realistic. And here's the most sobering thought. If we develop the technology and harness the resources necessary to terraform Mars, to literally transform an entire planet's climate and atmosphere, wouldn't we be better served using those capabilities to fix Earth's climate problems? If we can engineer planetary atmospheres and climates, solving Earth's climate change challenges becomes trivial by comparison. Earth has a thick atmosphere that needs modest adjustment, not creation from scratch. Earth has abundant water, thriving biospheres that naturally regulate atmospheric composition, and billions of people who already live here. Every argument for developing terraforming technology for Mars is actually an argument for first using that technology to ensure Earth remains habitable and prosperous. Let's return to the human element, because ultimately, colonization isn't about engineering challenges or economic calculations. It's about people choosing to leave Earth and build lives on another world. What kind of person volunteers for this? What motivates someone to accept lifelong exile from Earth? Perpetual danger, severe restrictions on personal freedom, and guaranteed hardship. Some would go for idealistic reasons. They believe in expanding humanity beyond Earth. They want to be pioneers. They're drawn to the historical significance of establishing the first extraterrestrial human settlement. These motivations are real and powerful. The first Mars colonists would certainly include people driven by such ideals. Others might go to escape problems on Earth, economic hardship, political persecution, lack of opportunity, or simply dissatisfaction with their lives. Throughout history, colonization efforts have attracted people seeking fresh starts. But Mars isn't the American frontier or a new continent with resources to exploit. It's a lifelong commitment to harsh conditions with no easy way back if things don't work out. There's a real risk of exploitation if corporations or governments recruit colonists with promises of opportunity that don't materialize, if working conditions are worse than advertised, if colonists effectively become indentured servants working to pay off their transportation costs with no real freedom to leave. We'd be recreating some of the worst aspects of historical colonization in a setting where escape is impossible. Labor rights, working conditions, personal freedoms, all these would be challenged on Mars. In an environment where survival depends on everyone performing their duties, where does individual liberty fit? Can you quit your job if you're unhappy? Can you refuse to work? How do you enforce labor rights when the entire colony dies, if critical systems aren't maintained? These aren't hypothetical concerns. Isolated work environments on Earth, remote oil rigs, fishing vessels, certain military installations, have documented problems with exploitation, abuse, and lack of accountability. When workers are far from legal oversight, when they can't easily leave, when small groups have disproportionate power, abuse happens. Mars would be the ultimate isolated environment with zero oversight and no escape.
Family life on Mars presents profound challenges we haven't adequately addressed. If people have children there, and any permanent colony presumably would, those children grow up in a fundamentally different environment than any human has ever experienced. Their physical development occurs in 38% gravity. Their psychological development happens in confined underground habitats. Their entire worldview forms in an environment of constant danger and resource scarcity.
These children didn't choose to be born on Mars. They had no say in a decision that defines every aspect of their existence. If Martian gravity permanently adapts their bodies such that they could never survive Earth's gravity, we've created a generation of humans who are trapped on Mars by biology. Is this ethical? Do parents have the right to make such a consequential decision for their children? Education on Mars would be extremely limited, especially in early colonies. Small populations can't support specialized teachers across all subjects. Children would likely learn through remote video instruction from Earth or AI-based systems. Social interaction would be limited to the small number of other children in the colony. Extracurricular activities, sports, arts programs, all the things that enrich childhood on Earth, would be minimal or non-existent. Adolescence would be particularly challenging. Teenagers need to explore identity, test boundaries, and gradually gain independence. How does this work in an environment where stepping outside without a pressure suit kills you instantly, where every resource is rationed, where the community is tiny and everyone knows everyone else's business? The psychological pressure would be immense. Dating and relationships in a small, isolated population create their own problems. With only dozens or hundreds of potential partners, romantic relationships become logistically and socially complicated. Breakups affect the entire community. The genetic diversity necessary to avoid inbreeding requires careful management if the population remains small for generations. We start getting into uncomfortable territory of potentially needing to regulate reproduction to maintain genetic health, another ethical minefield. Mental health services would be critically important but difficult to provide. Mars colonies would need psychologists and counselors, but with limited population, you might have one mental health professional for hundreds of people. Privacy for therapy sessions becomes difficult in close quarters, where everyone knows everyone. The stigma around mental health issues, already a problem on Earth, could be worse in an environment where being perceived as mentally unstable might affect your work assignments or social standing. And what happens when someone becomes seriously mentally ill? Earth has psychiatric hospitals, medication options, and the ability to separate individuals who pose danger to themselves or others. Mars has none of these options. A person experiencing psychosis or suicidal ideation in an environment where they have access to critical life support systems could endanger the entire colony. Yet forcibly medicating or restraining colonists raises serious ethical and human rights questions. The psychological stress of permanent confinement shouldn't be underestimated. Humans evolved as mobile creatures in diverse, changing environments. We're psychologically adapted to travel, explore, see new places, and experience seasonal and environmental variety. Mars offers none of this. You're in the same habitat with the same people seeing the same rust-colored landscape forever. Even vacation, a concept most humans take for granted, is impossible. There's nowhere to go. Virtual reality might provide some psychological relief, allowing colonists to virtually visit Earth environments, but it's a poor substitute for genuine experience. Study after study has shown that humans need nature contact for psychological well-being. Views of natural environments, plants, water, varied landscapes. These aren't luxuries, but psychological necessities. Biophilia, the innate human affinity for nature, is real and powerful. Depriving people of nature contact leads to measurable psychological harm. Some research suggests that even viewing images of nature provides psychological benefits, so perhaps high-quality screens displaying Earth environments could help. But this feels like applying a bandage to a wound that shouldn't exist in the first place. We're talking about deliberately putting humans in an environment we know is psychologically harmful, and then trying to mitigate the damage rather than asking whether we should do it at all. Let me share a perspective that might be controversial. Maybe Mars colonization, as currently envisioned, is fundamentally unethical. Maybe subjecting humans to lifelong radiation exposure we know causes cancer, to psychological stress we know causes mental illness, to physical conditions we know cause bone loss and cardiovascular problems, to isolation we know harms well-being. Maybe this isn't a noble pioneering venture, but a foreseeable human rights catastrophe. The counter-argument is that people would volunteer knowing the risks. Informed consent matters. If adults understand the dangers and choose to go anyway, don't they have that right? This argument has merit, but it assumes perfect information and free choice. Would colonists truly understand the long-term psychological impacts before experiencing them? Would they comprehend what it means to never return to Earth until they're actually living that reality? Can you give informed consent to conditions you've never experienced and can't fully imagine? And what about the children born there? They give no consent at all. Their parents make the decision that determines every aspect of their existence. If we determine that Martian conditions cause them harm, developmental problems from low gravity, psychological issues from confinement, higher cancer rates from radiation, we've deliberately created a population of harmed individuals. That's not ethical pioneering. That's human experimentation on a massive scale. I want to be clear. I'm not arguing against Mars exploration. Robotic missions to Mars have been spectacularly successful and scientifically valuable. Rovers like Curiosity and Perseverance have revolutionized our understanding of Martian geology, climate history, and the potential for past life. Orbiters have mapped the planet in extraordinary detail. Sample return missions currently in planning will bring Martian rocks back to Earth for detailed analysis. These missions are expensive, but worthwhile investments in expanding human knowledge. I'm also not arguing against human spaceflight. The ISS has taught us invaluable lessons about long-duration spaceflight, life support systems, and human adaptation to space environments. Future missions to the Moon could establish bases that serve as test beds for space technologies while remaining close enough to Earth for practical support and reasonable safety. These are achievable goals with current or near-term technology. What I'm questioning is the specific vision of permanent Mars colonization as currently promoted by companies and enthusiasts. The technical challenges are far greater than usually acknowledged. The costs are astronomical with no plausible economic return. The human costs in health, well-being, and freedom are severe and potentially unethical. And the timescales for achieving genuine self-sufficiency, if it's even possible, are measured in centuries. The romanticized vision of Mars colonies as a backup for humanity, as insurance against Earth catastrophes, as the next chapter in human expansion, this vision doesn't survive careful examination. A Mars colony wouldn't be independent of Earth for generations. It wouldn't save humanity if Earth civilization collapsed. It wouldn't be economically viable. And it would subject colonists to conditions that would likely cause serious physical and psychological harm. If our concern is truly the long-term survival of humanity and the expansion of human civilization, we'd be better served by different approaches. First and foremost, we should focus on ensuring Earth remains habitable. Climate change, biodiversity loss, nuclear weapons, pandemic risks, these threaten humanity far more immediately than any cosmic threats, and solving them is vastly easier and cheaper than establishing Mars colonies. For space development, we should prioritize incremental steps that build capability progressively, establish permanent lunar bases, develop closed-loop life support systems, and in-situ resource utilization there, where rescue is possible and supply lines are manageable. Build orbital infrastructure, larger space stations, manufacturing facilities, fuel depots, taking advantage of microgravity for processes difficult on planetary surfaces. Develop the technologies we'd need for Mars: advanced propulsion, better radiation shielding, reliable life support, efficient resource extraction, but develop them in contexts where failure doesn't mean death and where iterative improvement is possible. Only after we've mastered these technologies in more forgiving environments should we consider applying them to Mars. We should also invest heavily in robotic exploration and telepresence. Advances in robotics, artificial intelligence, and virtual reality could allow us to explore and even develop Mars remotely, with humans safely on Earth or in orbit controlling sophisticated robot systems. The communication delay makes real-time control impossible, but increasingly autonomous robots could operate on Mars with human oversight, performing much of the work without exposing humans to danger. If we eventually develop technologies that genuinely solve the fundamental problems, artificial gravity through rotating habitats, truly effective radiation shielding, manufacturing capabilities that allow real self-sufficiency, psychological interventions that mitigate isolation effects, then Mars colonization becomes more feasible. But we're not there yet, and pretending we are does a disservice to the genuine challenges involved. The enthusiasm for Mars is understandable. It captures the imagination. It represents exploration, adventure, and the expansion of human potential. The desire to reach beyond our planet, to explore new worlds, to ensure humanity has a future beyond Earth, these are noble motivations that have driven exploration throughout history, but enthusiasm must be tempered with realism. The actual Mars, not the romanticized vision, but the real planet with its thin toxic atmosphere, intense radiation, extreme cold, and comprehensive hostility to human life, presents challenges that aren't solved by optimism and determination alone. They require technology we don't have, resources on a scale never before marshaled, and time frames spanning centuries. Perhaps most importantly, we need to ask whether Mars colonization is truly the best use of resources and human potential. The hundreds of billions or trillions of dollars required to establish even a marginal Mars colony could alternatively fund solutions to Earth's problems, develop sustainable energy systems, cure diseases, improve education globally, or advance technologies that benefit the billions of people already living on a planet we know supports human life. The argument that we can do both, solve Earth's problems and colonize Mars, sounds appealing but ignores practical resource constraints. Money, political will, scientific expertise, and engineering capacity are all limited. Choosing to direct enormous resources toward Mars inherently means not directing them elsewhere. Opportunity costs matter, especially when the opportunity being foregone is addressing pressing problems affecting billions of people right now. I realize this entire discussion has been deeply skeptical, even pessimistic. That's intentional. The predominant narrative around Mars colonization tends toward uncritical enthusiasm. Companies promote visions of thriving Mars cities. Enthusiasts share artistic renderings of terraformed Mars with blue skies and flowing rivers. Popular science communicators emphasize the exciting possibilities while downplaying the sobering realities. We need balance. We need clear-eyed assessment of what Mars colonization actually entails. The dangers, the costs, the sacrifices, and the extremely long time frames before anything resembling the popular vision might be achievable. We need to acknowledge that it might not be achievable at all, or that by the time we develop the necessary technologies, we might have better options. None of this means we should stop dreaming about the stars. Human curiosity and our drive to explore are among our best qualities. But dreams should be informed by reality. The path to becoming a spacefaring civilization likely doesn't run through Mars, at least not in the ways currently envisioned. It probably runs through incremental development of space infrastructure, mastery of technologies in more forgiving environments, and patient accumulation of capabilities over generations. If and when we eventually establish a genuine, thriving human presence beyond Earth, whether on the Moon, Mars, orbital habitats, or elsewhere, it will be because we took the time to do it right, solved the fundamental problems rather than hoping they'd resolve themselves, and made decisions based on careful analysis rather than enthusiasm alone. Mars will still be there in 100 years, in 500 years, in 1,000 years. It's not going anywhere. When we're truly ready, when we have the technology, the resources, the understanding, and the wisdom to do it responsibly, Mars will be waiting. Until then, perhaps we should focus on taking care of the one planet we know for certain can support human life, while gradually, carefully, developing the capabilities we'll need when the time truly comes to reach beyond it. The universe is vast, ancient, and patient. Humanity is young and impulsive. Sometimes wisdom lies not in rushing toward the seemingly achievable, but in recognizing which challenges require more preparation, more technology, and more thought before we commit lives and resources to attempts that might prove tragically premature. Mars represents a magnificent challenge and a worthy long-term goal. But between the dream and the reality lie chasms as vast as the space between worlds, and crossing those chasms will take longer, cost more, and require more than most advocates currently acknowledge. If you found this deep dive into the realities of Mars colonization thought-provoking, you won't want to miss my previous video where I explore an even more fascinating scenario. The video is on the screen. What happens when we find the perfect planet for humanity, only to discover we're not alone? This one is a must-watch.